Hello everyone, it's great to be here. Thank you for listening. My name is Thomas Vasen, I am from HMS Networks and I'm the product manager for OT Network Security Solutions. You might know us better as Anibus or E1, and we recently merged with Red Lion Controls and Entron, an exciting step for us to strengthen our industrial offering. Personally, I'm Dutch, but I've lived in Sweden, where HMS is headquartered, for almost 30 years. I've worked with security solutions focused for about 10 years or so, but before that I came from the telecom space. 10 years at operators and 10 years at specialized vendors. I'm grateful for that background, as it has given me the 5-9 DNA. Uptime is nowhere more important than in telecommunications, while at the same time every bit and second counts, as it's worth money. And as a customer, you trust the integrity of the network when you, for instance, see a caller ID. This mindset, I believe, gives the ideal background to work with other critical operational systems. Today, I want to talk about defending uptime with OT-SDN segmentation strategies. It's about building security inside the network, where it should have been from the beginning. Before we begin, I want to highlight a bit what we are doing this for. OT attacks are on the rise and they result in significant impact in people's lives. Examples of this are the Triton Trisis Safety Systems attack 2017 in Saudi Arabia. Someone supposedly wrote the virus specifically targeting Schneider's safety control system in Saudi Aramco's oil refinery. They specifically manipulated the systems with the purpose to cause massive explosions. Luckily for us and the world, they made some errors in the code that caused the malware to malfunction. It's almost like they were experimenting. But the results could have been catastrophic. It was a true wake-up call. Colonial Pipeline's ransomware attack in 2021 was very impactful as OT had to shut down and gas was not distributed to the pumps in the northwest of the USA. A typical IT attack with major OT consequences, as many of them are. Also the very recent in the United Kingdom at Jaguar Land Rover. The Modbus attack on building heating systems in Ukraine during the winter of 2024, that was truly awful. Here, the Russians manipulated the PLCs by using normal Modbus commands and turned off the heating for 600 apartments while outside temperatures were sub-zero. They did this on purpose, as the access hack to the network was later traced back to April the year before. So why does security fail in industrial networks? Let's be honest, security is still too often an afterthought. Networks, especially in industrial environments, have traditionally been designed for speed and availability, not security. This is especially true in manufacturing. The World Economic Forum highlighted this in a report already a few years ago, naming that manufacturing is the most targeted sector for cyber attacks. It's been like this 4 years in a row now. Why? Because manufacturing has embraced rapid digitization to improve efficiency, sustainability, and enable Industry 4.0. But this transformation comes with a cost. Manufacturers also tend to have a high willingness to pay when downtime does strike, because the impact is so huge. And that, of course, has made them a prime target for attackers. It is important to understand these threats are real. While some still are IT threats, they reach deep into the OT environment and are getting more focused. It is no longer theoretical. Gartner predicted that this year cyber attacks would have a direct impact on human safety, if that has not already been the case. But attackers are mostly financially motivated, and now malware is evolving specifically for OT environments because it's more impactful and frankly more effective. The consequence? Cybersecurity vulnerabilities in OT are becoming a safety risk. That's why it's no longer optional. Implementing robust IT security is a necessity. But change is not only driven by threats, it's also being pushed by regulations. In Europe, the NIS2 directive went into effect last October. It requires proactive action from executive teams, and also manufacturing is now officially designated a critical sector. Together with the upcoming Cyber Resilience Act that requires products to be secure by default before they can be sold to the market, this promises a much more secure world. But relying on devices getting into shape to provide protection, is this really the answer for our existing environments? Is waiting for regulation really the answer? We already have excellent frameworks like IEC 62443, which helps harden infrastructures and guide best practices. But there is a challenge. These frameworks are still often optional, and they take time, strategy, and maturity to implement properly. So before we dive into solutions, let's take a step back. How did we get here? Why is the status of security for physical systems the way it is today? Let's start with an industrial security reality check. Digitization changes networks. At HMS, we follow the trends with regards to industrial protocols very closely. And it tells a story of how networks are evolving. Traditionally, industrial networks were built as isolated air-gapped systems. They often used technologies like serial buses, which made it harder for outsiders to interfere. Sure, a hacker could target a PLC, but to disrupt the physical process, deep knowledge was needed. Stuxnet, as a well-known example, but successful attacks like that have really been rare. However, as we've seen in our annual HMS Industrial Protocols report, networks are rapidly evolving. Industrial systems are increasingly built on standard Ethernet, using IP as the underlying transport protocol. To stay air-gapped, many networks have been designed with multiple interfaces on a PLC, forcing traffic to bridge through it, mimicking the old serial bus model. This design may limit some threats, but it doesn't eliminate them. Other Ethernet-enabled devices can still connect physically to the network, directly or via remote access, increasing the threat service. Physical access was once a high barrier, and now it's often just a cable away. And more critically, this approach blocks innovation. For true digital transformation, new tools need access to both networks and assets. So networks are changing. The PLC becomes just one node on a broader, more open architecture. Other systems are granted access directly towards the industrial network. This opens access enables faster digitalization, but it also comes at a cost. A much larger threat surface and an increased risk for downtime. Miscellaneous actors now have the potential to access through the IT infrastructure. In short, unifying network technologies has enabled innovation, but also increased risk. And now this balance must be managed very carefully. The result right now? Incredibly open flat networks like these. These are diagrams of discovered architectures of operational networks with cyber physical systems. This is very alarming. In networks like these, a single threat can come from anywhere, and once inside, it spreads like wildfire. Why? Because there's no segmentation, no containment. We see this far too often, and frankly, it's a huge risk. Why are flat networks so dangerous, you might ask? There are several contributing factors. One major reason is the widespread use of Windows in industrial environments. Windows is a great platform to encourage rapid development, but also as a multi-purpose operating system, it's very hard to harden. Can you really reboot an entire factory every patch Tuesday? In telecoms, we had one rule: never ever no Windows in operational network. It's too risky for the uptime. In industrial networks, this has not been a key principle. But it's not just Microsoft's fault. Another major issue is the long lifespan of industrial systems. We still encounter machines running Windows 95 or even DOS, kept alive by hope, with no support, no updates, no spare parts, no recovery plan. This is a fundamental mismatch. OT systems are expected to run for 20 to 30 years, and IT systems are considered outdated after just 5. A major contribution is also poor access control. Lack of personal accounts for login, poor passwords on shared accounts, and not using modern technologies like multi-factor authentication down on the shop floor. All this makes it easy for the adversary. And we must also admit, it's not only Windows being vulnerable. Research shows that the average CVSS score, that's the severity score of items logged in the Common Vulnerability Database, shows that for vulnerabilities on products used in manufacturing sector, there is statistically a 33% higher severity than the global average with products used in other industries. In other words, devices used here are basically poor designed from a security perspective. EU's CRA will help here over time, but for now, everything built before 2028 mitigations must be designed in the network architecture. And lastly, very important, the inherent design of industrial protocols, like Profinet and Ethernet IP or Modbus. They do not have authentication built in. Anyone with access to the network can manipulate the control systems. And this is made easier and easier with available tools and pre-made scripts in hacker frameworks. And of course, with AI. There is not much special and inaccessible about industrial protocols anymore. And let's not forget, uptime isn't just threatened by cyber attacks. It's also at risk from faults, errors, and even simple mistakes. Downtime can result from misbehaving equipment or aging components, poorly configured or overloaded networks, physical issues like damage to low-quality cables, insider threats, both accidental and intentional, the oops factor, and yes, also cyber attacks, not to underestimate. To truly defend your operations, you need a solution that protects your infrastructure and uptime no matter the cause of disruption. Security should really have been embedded inside the network. So let's discuss solutions. The promise of segmentation. As a wise hacker once said, if I can't reach it, I can't attack it. Segmentation creates boundaries. It limits the blast radius. By isolating systems, we reduce the attack surface and contain potential threats. It's a simple principle, but a powerful defense. It's the core of any protection strategy. Segmentation between networks, between machines, and ultimately between individual assets. Of course, you already have the enterprise firewall between the internet and your office IT network. Its job is to stop unwanted traffic from coming in, but also allow outbound traffic so employees can use the web and cloud services and do their work. Next, you should separate OT from IT. Following defense in depth best practices, this firewall should be from a different vendor. Also, because the job to be done here is very different. In OT, you need to be very restrictive in both directions. Threats can come from anywhere, from visiting contractors, from remote access, neighboring machines, insiders, and of course from IT. This is exactly why asset owners are advised to isolate critical machines. Build walls around them, make them self-sufficient, and form smaller, manageable islands inside your network. As small as possible, while still practical to operate. This is a strategy that delivers protection, visibility, and control over your traffic and your production processes. The IEC 6244333 standard is an excellent source of guidance. It defines the security requirement at a system level. Requirements that can be applied to machines, lines, or entire plants. It starts with the impact analysis of each system or machine. You evaluate what the consequences would be if that system were compromised, whether in terms of safety, production, or business continuity. Based on this analysis, you define target security levels for different zones in your network. You then separate these zones using conduits, controlled paths that enforce your security policies. Typically, a conduit is implemented with an industrial firewall. It's a great strategy, but in practice, many teams struggle with what it actually means and how to apply it effectively in their own environment. What does it actually require? Standardization helps a lot here, in particular 62443. Let's break it down, starting with requirement 5.1 network segmentation. This stipulates separating control systems from non-control systems, isolating critical control systems, and separating machines based on their required security levels. Examples of control systems are PLCs with their drives. Non-control systems can be cameras for visual surveillance. And critical control systems can be safety PLCs or engineering workstations. This is a requirement for security level 1, the lowest level. This is followed by a core principle. Deny by default, allow by exception. Only allow specific necessary traffic that is explicitly required for the process to function. These controls are mandatory for security level 2 and above. And SL2 is generally seen as the minimum bar for secure industrial system design. In summary, segmentation according to this standard requires conduits between zones with strict monitoring and control of interzone traffic. So how do we actually implement segmentation? There are several technology options, each with different trade-offs. One approach is to air gap, use diodes or protocol gateways or couplers. These allow only specific industrial traffic through, blocking everything else. While this can enhance isolation, it also limits visibility and flexibility, making it suitable only for very specific use cases. A more traditional approach is using VLANs for a logical segmentation. This is very common, it requires managed switches, and for traffic policy, they require a separate enforcement point. A more robust option for security level 2 is using firewalls. This provides physical separation and enables deny by default policies to strictly control interzone communications. And finally, the most modern method, OT-SDN, software-defined networking. This enables centralized orchestration of segmentation, making the network programmable. You can define traffic security policies per device, achieving true microsegmentation and embedding security directly into the network infrastructure, as it should have been from the start. The most popular one of these is using VLANs. Let's walk through on how this works. VLANs require, as mentioned, managed switches. A managed switch must be configured to assign specific ports to specific VLANs. This enforces logical separation between devices, even if they share the same physical switch. Access control policies on the switch determine who can assign ports to what VLAN, and each VLAN usually represents a zone in your architecture. Any traffic that needs to move between zones, or between VLANs, must go through a routing point. And at this point, you can apply security policies to restrict or allow traffic based on higher level information. This is often done using a firewall that enforces traffic rules between the zones. This setup provides the foundation for security level 1 in 62443, meeting the basic requirement of logical segmentation for your network. Scaling this up makes things difficult. Every switch needs its own static configuration, fixating ports to VLANs. Your security zone configuration is completely distributed. And the communication policies are distributed on all the firewalls serving these zones. It's very hard to keep control of security postures like this. In addition, this traditional segmentation falls short in one major way. It focuses heavily on north-south traffic, traffic flowing between IT and OT layers or between the zones, but completely ignores east-west traffic, traffic within the OT network itself, where lateral movement often happens during an attack. Architects usually refer to the Purdue model and say that segmentation is done between the different levels, between the level 1 hosting the physical process and level 2 hosting the supervisory control systems. But this is not a good security model, it's a reference architecture. Not everything in level 1 should be open towards each other. This is why zones get smaller and smaller, but this becomes very complex to manage. Not to mention that it's an absolute pain to implement in brownfield installations. To defend against today's threats, we need dynamic segmentation, a solution that helps implementing segmentation easy and that protects both between and within zones. Introducing OT-SDN, software-defined networking for microsegmentation. OT-SDN brings zero trust principles into industrial networks, enabling security that both is granular and automated, as well as vendor independent. Key capabilities of software-defined networking for OT include a centrally orchestrated programmable network with an independent software in the control layer talking to multi-vendor standardized infrastructure layer, providing deny by default rule set so that new devices are blocked from all ports unless explicitly allowed, providing tight traffic control. Only approved protocols between specific devices, no unsolicited traffic. It is completely designed for industrial needs with uptime in mind. No central dependency for normal operations. Automatic rerouting if a path between endpoints fails. And security posture rebalancing if a device is moved. Security policies adjust automatically. OT-SDN networking enables zero trust network access with a single point of management, providing real-time insights into what's on the network. It allows precise control over which devices can communicate and with what protocols, while still being multi-vendor compatible. What makes it OT specific is that it also includes device identification, not just traffic control. Let's see how this works. It starts with OpenFlow compatible switches. These work much like managed switches, but they support the open source OpenFlow protocol. You can use what you have if it supports the protocol or replace like for like number of ports with an SDN switch without changing your network architecture at all. These switches connect to a central orchestration controller. All network access requests go through this controller. Device identification themselves, typically by MAC address, but the controller can go further. For example, it can use Ethernet IP SIP polling by requesting additional information like the device's serial number. Once the device is identified, the controller assigns traffic policies to that specific device. The policies are then pushed to the switches. From that point on, the switches enforce the policy locally. Traffic does not depend on the controller once it's flowing. You can define exactly what is allowed. For example, traffic from a specific PLC to a specific robot using only approved protocols. Let's have a look. A PLC is plugged into the network for the first time. A request is made to the controller asking about the policy for this newly detected device. It installs the policy to allow SIP traffic from the PLC to the robot on port 44818, MAC address to MAC address. All other traffic of different types or from different nodes will be denied. Zero trust. Perhaps more connections are needed, like OPC UA to the HMI. If the policy is not already implemented, the lookup will go the same path and the policy will be updated in the switches. Thereafter, traffic does not need to check with the controller again. But the controller is constantly informed about how much traffic of what type is sent where. If someone plugs in a new device, say a visitor's laptop, it's immediately denied access, even if it's on the same port a PLC was using earlier. If traffic mirroring is desired, for instance towards a central security monitoring solution, the SDN controller can network-wide decide what flows should be copied where. It makes it a breeze to gain insights into larger networks. No more local spam ports and taps needed. OT-SDN gives you simplified networking and maximum control. It provides microsegmentation at the device level. It enables dynamic security policies. It gives real-time visibility. And it allows for smart monitoring feed, all while being compatible with any OpenFlow switch. Let's have a look at how this looks like in a GUI. Here you see a network automatically being drawn up. You see 4 switches creating a ring network, and on each different endpoints are detected automatically. Now select the engineering PC and the PLC, and then you are able to configure the traffic rules of what flows can travel between these nodes. In this example, I have ICMP and SIP. It also has the observed traffic, only showing what was reported happening on the link between these two devices. Looking from different perspectives, including manageability, how much insight into traffic is provided, the operational resilience of the solution, the security, and how easy it is to implement in brownfield scenarios. Each method has their strength, but it's clear that the most common method, logical segmentation using VLANs, is the weakest one of them all, particularly on manageability, but also on other aspects. Strongest is for sure orchestrated segmentation with SDN, finally providing a way to implement strict traffic policies inside brownfield networks without having to redesign the network and readdress all the devices. It's simply done by central orchestration, through graphical configuration or automatic discovery of traffic patterns. In conclusion, it is in today's world incredibly important to pivot from reactive to proactive security, both to protect against cyber threats, but also against other operational threats. You must build segmentation into your network design, and there are several options available for you. You must choose the technology that helps you make this easy. OT-SDN can help change the game on how this is managed, resulting in improved uptime. Thank you very much. If there are any questions, please connect to us on LinkedIn or contact us, and we'll be happy to engage in a dialogue.